Hello, this is the first video of the fifth complex number series on complex roots for the OCR Pure Core Further Mathematics, and the title is Solving z to the n equals 1. Solving quadratic equations was covered in a previous video. You should know these have two roots which may be real. So, for example, there's a root there and there, or a repeated root. And let's do an example here where we have you bounce off, so that repeated root is there, or two complex roots which will form a conjugate pair. So you might have a curve which looks like it has no roots but just means it's got no real roots. Just to remind ourselves using a quadratic example, if we are asked to solve a quadratic equation z squared minus 2z plus 5 equals 0, we could rearrange this or use the quadratic equation to find that z equals 1 plus or minus 2i. Remember, complex roots from a quadratic equation will always occur in conjugate pairs, which we denote by z and z star. We can choose either to be the z, but the other one will then be z star. So here, let's choose z equals 1 plus 2i, then z star would be 1 minus 2i. You will also have solved cubic equations to find three roots, some of which may be complex. Let's have a look here, sketch what sort of the options might be for a cubic curve. So we might have three real roots, there, there and there, or you might find that you have a repeated root. It just bounces off. So there's one real root and there's your repeated root there, so two roots there. Or we may find that you have a complex conjugate pair of roots, and then you're always going to have one real root though because of the shape of the cubic curve. So every polynomial equation of degree n has exactly n roots. It may not be apparent when we sketch the graph because some of these may be complex numbers. These complex roots will always occur in conjugate pairs. If we go on to sketch graphs for quartics, again we'll have an option where we might have four real roots. We could have an option where we have two repeated roots. We could have an option where we've got a complex conjugate pair of roots and then two real roots. We could have two complex conjugate pairs of roots, and so on. You may wish to do more sketches on your own and check all the different options. Even the simple equation z to the n equals 1 has n roots. Now one of these roots will be z equals 1, and if n is even, then another will be z equals minus 1. All the other roots will be complex numbers, and these can be shown on an Argand diagram, similar to the ones shown in the two diagrams below for z cubed equal 1 and z for 4 equal 1. For the equation z squared equals 1, you could write this as z squared minus 1 equals 0, and then factorize that to being z plus 1 times z minus 1 equal to 0, thus leading us to the two roots of 1 and minus 1, as shown here. For z cubed equals 1, we could again write this as z cubed minus 1 equals 0 and factorise z minus 1, z squared plus z plus 1 equals 0. The roots are therefore 1, and we would find the other two roots by using the quadratic equation to be minus 1 plus or minus root 3i over 2. For z for 4 equals 1, we could factorise this to being z squared minus 1 and z squared plus 1. We know that z squared minus 1 can then be written as z plus 1, z minus 1, leading to the two roots plus or minus 1. Z squared plus 1 can be factorised z plus I, z minus I, leading to these two roots here. Let's use GeoGebra to look at these in a little bit more detail. So when n is 2, you can see that there's a unit circle and the two roots lie on that unit circle. For n equals 3, you'll notice the three roots again lie on a unit circle and form an equilateral triangle. For n equals 4, they again lie on the unit circle, as one would expect, but form a square. You note that these are all regular polygons. So here, for n equals 5, the roots of z for 5 equal 1 lie on a unit circle and are the points of a regular pentagon. For 6, similarly, but for a hexagon, and so on. For 7, for 8, and so on, up as far as we wish to go. Note that the angles between the roots will decrease, but the modulus of those roots does not change. That always remains 1, and that's why the points lie on the unit circle. In the next video, we will look further at the nth roots of unity.